Chemistry, the Central Science, Chapter 7, Periodic Properties of the Elements, Lesson 2. So in the last lesson, we looked at ionization energy. So electron affinity is the opposite of that. Electron affinity looks at how much do you like to get electrons, right? Affinity is how much do you like something. So electron affinity is the energy associated with receiving an electron to become an anion. So here, this shows a generic equation of an element accepting an electron to become negative. So for example, when fluorine accepts an electron, it gives off 328 kilojoules of energy. If oxygen accepts an electron, it gives off 141 kilojoules of energy. So elements that like to accept electrons are going to give off energy because it is a favorable process. They're becoming more stable. Elements that do not want to accept electrons will not. So in looking at our trends, we can see that our highest electron affinities are associated with our halogens, giving off the most amount of energy. And then we notice that both group 2 metals right here and noble gases have a positive electron affinity because you're trying to force electrons onto something that already has filled shells like the noble gases or filled subshells like group 2 metals. But our general trend is that as you move from left to right across the periodic table, the electron affinity increases, so it becomes more negative. As you move down the periodic table, it is less. So our highest electron affinity is actually chlorine, so our halogens have our highest electron affinities. Our noble gases are positive, they do not want to accept electrons, and then the trend varies. So the last thing to look at in terms of trends is metallic character. So as we move from left to right, we become less metallic, right? So our metals are on the left side of the table, our non-metals are on the right side of the table, and then they're separated by some semi-metals. So typical characteristics of metals is they tend to be solid at room temperature, except for mercury. They're good conductors of electricity. They tend to be malleable and ductile. They're good conductors of heat, typically. Non-metals are just the opposite. They can be solids, liquids, or gases, not good conductors of electricity or heat typically. And metalloids are somewhere in between. So they have properties of both. So how can we use some trends to look at main group elements and how they react? So ionization and electron affinity are really great to tell us what kind of compounds might form, right? If you look at the ionization energy of sodium, the electron affinity of chlorine, we see that sodium likes to give up an electron, chlorine likes to accept it, and then we can form sodium chloride. So oftentimes when we look at our ionization energies of our metals, our electron affinities of our nonmetals, it gives us a good idea about what kinds of compounds can be formed. And so now we're going to look at the groups and just some general properties of our groups or families, right, in our columns. So group 1A elements have an extremely low ionization energy. They're never found in nature in the pure elemental state, and they react with oxygen to form metal oxides. They are very soft. They're highly reactive to water. So when you store pure sodium or potassium or cesium metal, it has to be stored underwater, or it's not underwater, in oil, mineral oil. So your group 2s are not as active as your group 1s. Some of them can react with water to produce hydrogen as a gas. Some are not reactive with water, and instead you have to dissolve them in acid to produce hydrogen as a gas. So comparing group 1s to group 2s, group 2s are not as reactive, but we know that they still like to give up electrons and can form compounds with nonmetals. These you can find in nature by themselves. So hydrogen is special. Hydrogen is unto itself. Why? It's in group 1 with the metals, but it's not a metal. Sometimes you can see it stuck over with the halogens, but it's not a halogen. So typically what we see is hydrogen forms a cation when it is bonded to other nonmetals. It forms an anion when it's bonded to metals, and that's called a hydride. So hydrides react with water to produce hydrogen gas and water. So other main group elements, we can look at oxygen's group number 6. We know that oxygen exists as diatomic. Sulfur and selenium are crystalline structures, soft molecular solids. Then we have some metalloids, and then we see that sulfur can react with oxygen in different ways and forming hydrosulfuric acid and sulfuric acid, which can cause acid rain. So most of our elements, sulfur, selenium, will react to form acids with water. Our halogens are all diatomic. They do not exist in elemental form in nature all by themselves, is what we should say, because they are diatomic. They tend to form bonds with other substances. They really want to get electrons. So they form ionic salts, right? Your group 7 halogens really like to react with your group 1 metals. And then they can form molecular compounds with each other. And they react with hydrogen to form hydrogen halides, which is also known as acids, right? Hydroiodic acid, hydrobromic, hydrochloric, hydrofluoric, etc. Lastly, looking at our noble gases, or group 8, they're all monoatomic, so they're always found in nature all by themselves. They have completely filled valence shells. They were considered inert, meaning that they didn't react, which is why they used to be known as the inert gases, but then it was shown that when fluorine was introduced to xenon and krypton, compounds could be formed. No major commercial use except for when we think about helium. Helium is used to fill up balloons. We have a hard time getting a hold of more helium. It's something that is a byproduct of nuclear decay. Not that helium itself is radioactive, but alpha particles that come off of elements that are undergoing nuclear decay, right? An alpha particle is a helium nucleus. As long as it picks up some electrons, now you have helium. So we have to go around and figure out where we can find helium in the ground next to radioactive substances. So comparing group 1A and 1B elements. So both of these elements have single valence electrons, but their properties differ. Group 1B is much less reactive than 1A. And when we're talking about 1B, we're looking at, it's silver, copper, and gold. So they have all these d electrons that are shielding the nucleus. Your valence electron is still your outermost shell, but they're just not as reactive because they have all of these d electrons. So 1B metals are often found in nature, your coinage metals. They're called coinage. Why? Because we make coins out of them.